present from slide.
Now you're unmuted.
Oh, wow. Hello.
Welcome back after the lunch break. So we will head to our afternoon sessions. And the first speaker is an invited speaker, Francesca Miozzi, and with her we make a deep dive into Planetary Interiors before we go to the breakout sessions. The floor is yours.
Thanks. Thank you very much for being here after lunch. I hope this will be fun enough that no one falls asleep, but we will see. So I am Francesca Miozzi. I'm a postdoc at Carnegie EPL. And today I want to sort of seeing a lot of things that have been already said during all the other presentation, but from a mineralogical perspective. So not even an interior perspective, but really going deeper into what we can consider, what we need to be considering. So let's start with something that we have seen in a very big amount of flavors, but let's say that the idea is that we observe a planet. This guy, Planet X, like a random planet, not Planet X of the solar system. And so we have a mass, a radius. We might have a sort of compositional sign from the atmosphere. How do we know how it's made inside? The way in which things are being done now is to sort of think about which kind of interior we might have, plot the evolution of the mass and radius for such interior, and see if our mysterious planet fit in here. However, what I want to bring the attention to that hasn't been really discussed in these days is the time variable. So when we are looking at this planet, we are looking at a snapshot of an evolution that might look like this if it's an Earth-like planet, for example. And we see that this is a very complex history of interaction between the interior, between the atmosphere, and processes going on. And when we look at exoplanets, we don't really know where we are looking. We don't know if we're looking here, here, or here. We can have a sense, depending on atmospheric composition, for example, or age of the star, if we can get the age of the star, but we don't really know. So today, the other things that I want to discuss is that for what we have seen in these days, sometimes people might be led to consider maybe just the volatiles for the atmosphere. So we are considering these aspects. Or we might be considering the solid to make mass radius plots. So we are considering these aspects. So which kind of interior I can get. What I want to convince you today is that we really need to go farther and start speaking with each other and go toward integrative model that include all the layers. Because planets are dynamic, all the layers in planets speak with each other. And so let's take this figure and analyze sort of the evolution in time. We start with the initial phase of formation. We don't even have a core. We are forming a core. Everything is in the molten state. We might have some ingassing, some outgassing. Let's consider the surface. I draw here this very sharp boundary. Reality is that this boundary might not even be sharp. So we don't even have a sense of how this boundary between atmosphere and interior can be. But we know that we can sort of bring volatiles in. And so these volatiles will be in this that I want to specify it's a melt. So it has different properties from the solid behave in different way, and it's really hard to represent experimentally, and I think also modeling, there are still a lot of things that we need to constrain. So we have volatiles here, but they don't just stay here. Also, sorry, volatiles can be as bubbles or can be incorporated in the structure of the melt. And in this case, we're speaking about solubility of flight elements in a melt. So in this case, we can also have chemical reaction that interact with these volatiles. Then we go slightly deeper. We are starting to separate a metal to form our planetary core. Volatiles can go in this metal. So these mean that these droplets that go toward the core can act as a sink. And this is a very simplified version of the processes. So don't take it as this is the Bible of what's happening, but I wanted to give a sense of what's going on with elements inside the Earth. And there is another variable that we need to consider. Properties of the melts, all melts, so the silicate melt, the metallic melt, they change with pressure and temperature. So the amount of stuff that we can store in here is likely much different from the amount of stuff that we can store in here, for example. And these lead to a very interesting scenarios also in terms of dynamic aspects. But let's say now we go to the next phase. So we start going deeper. And we reach this moment in which we have solidified a core, we have separated a core that is still molten. And so we have this silicate layer. So this is one of the most important moments in the evolution of a planet, because as Seth said yesterday, accretion matter. This is the moment in which everything gets set. And in this moment, we have a big liquid pool that interact with the atmosphere. And this layer controls essentially how we transport it outside the planet. So how the planet cool down and which kind of dynamic style we can have. But what controls this? What controls this heat transport? Properties of the melt, not only here at the interface with volatiles, but also in depth. So now the next question is like, what do we know about these melts? What can we say? Do we know something? The answer is yes. We actually know a lot about how volatiles and melts interact, because this problem has been approached from the Earth side for a very long time with many different flavors. We have complex volatile in subduction zone. We have modeling of like magma chambers in which we have these bubbles that might solute or not. But what is the problem? The problem is that is not really a problem, but why we can't use these data as they are? We can't because they are made to represent more evolved melts. So melts that have lived through through all the evolution of the Earth, and gases that are sort of like I know people around here maybe don't like the term secondary atmosphere, but gases that sort of belong to a more evolved atmosphere. What we are missing from like our knowledge is what happened to primitive composition of melts, so like magma oceans, and hydrogen. And this happened because working with hydrogen is a pain. Let me tell you, I'm one of those people doing it now experimentally, and it's really hard. And so for the moment, we didn't have the technological capabilities for doing it, and we didn't have the interest. We were focusing on interpreting the Earth as it is now, but because the exoplanet science wasn't really still existing, because it's in recent year, we have capabilities to see atmosphere and so on, there was little attention on such a simple gas. So now there are more people working on it. There are Paolo, Maggie, there is Cara Brookman, who was supposed to give a presentation today, but she's not here, unfortunately, and myself, who are trying to sort of define what hydrogen does. But let's keep on going in our evolution of the Earth, or of our planet. We sort of go from this magma ocean phase to where we start solidifying. And the chemistry of the magma ocean phase, so which elements I have here, controls what I'm getting. So the mineralogy of the forming phases and the thermal and physical properties of these phases control which kind of mantle we're getting. So what I'm trying to convince you is that whatever happened in this phase is what ultimately control if we're going to evolve in a dynamic planet like the Earth with subduction zone and so on, or like a sort of stagnant lit, but maybe not really stagnant planet like Venus, or something else that we don't even know because we don't have solar system examples. So ultimately, the properties of melt and the properties of minerals really control what's going on inside the planet. And we have seen in this past day that we can make like super complex model, very interesting stuff. But I'm an experimentalist. So what I want to show today is the capabilities of experiments, what we can do, what we have done so far, but also where are the pitfalls, like where we need to be careful when we are looking at experimental data to use for modeling or like to extrapolate information. So there are a lot of experimental techniques we can use. We have now the capabilities of going really deep into planetary interior. And I have here the two main experimental techniques that we can use. So we have temperature over pressure, and we can use large volume presses where we squish samples with a potentially very big volume. And here we are limited up to like 50, 40 GPa. There have been cases in which people went to like 100 GPa, but that's not the routine. And then we can use diamond anvil cell. And with diamond anvil cell, we can routinely reach 200 GPa. So to give you a sense, sort of like the equivalent of the liquid outer core in the Earth. And there are now advances that allow us to go even farther than 200 GPa. And we will see the presentation from Federica later when she will show what they can do with shock compression. But so what happens when we do experiments? The idea is that we want to represent the pressure and temperature conditions that are inside the planet with our samples. The way in which then we work on the samples, there are millions of them here. I just want to focus on the fact that we can study sample ex situ, so after the experiment. So the sample is studied at ambient pressure and ambient temperature, or we can study sample while they are at high pressure and high temperature. So these are like in situ experiment. I have here the example of X-ray diffraction, but there are a million other techniques that you can use. But the idea is that here, our sample will be at ambient pressure, at ambient temperature when I'm studying it. Here, it will be still at high pressure and high temperature. And this is really fundamental, and I will show you later why. So what do we want to get? What's the main point, what we can get? The idea is that with ex situ experiment, for example, at electron microscopy, we get information about which phases are stable. So how the elements divide into mineralogical phases. And we can do it for large volume experiment as this one, or we can do it from diamond and mill cell experiment. This is an experiment recovered for like 200 GPa. And on the other hand, if we make in situ experiments, we are more looking at how atoms are organized, so unit cell volume. And we have access to the properties, so the volume, for example, of a single mineralogical phase or multiple mineralogical phases in the entire pressure and temperature range we are considering. But what do we do with this data and why are they important? So let's start with ex situ experiment. I told you we have information about which are the stable phases. I have here an example from one of my publications. These two figures are pressure on the x-axis and temperature on the y-axis. All these points are single experimental points. So each one of these was a sample loaded in a diamond and mill cell and compressed to this PT condition. And what I want to bring to your attention now is the fact that in this phase diagram, here we have iron plus liquid. In this phase diagram, here we have FeSi plus liquid. And this is one of the fundamental aspects. So we want to know which phases are stable because we want to know what happens when we go in temperature and maybe one phase melt before the other. And so we have one solid phase in equilibrium with a liquid. And why it's so important? Because this is a representative of what happened instead when I cool a planet. When I'm cooling a planet, I'm going down in temperature. So knowing which is the last phase to melt, tell me what is the first phase that will crystallize in a magma ocean, in a planetary core, if you're speaking about metal. And from these, we can start deducing some of the fundamental properties of planetary interior. So how did we apply, for example, this data? We applied it to a potential core crystallizing in an iron silicon carbon alloy. We saw here the last phase to melt is iron. So this means that when we cool the planet and we start crystallizing something, we will crystallize pure iron. Crystals are denser than the liquid, so they will sink down in the core. When they are sinking, they induce a change of chemistry in the remaining liquid that in turn can be considered as an efficient force for a geodynamo, a driving force for a geodynamo. That is what starts a magnetic field in a planet. This is the example of the Earth, and we know we have a magnetic field. Now, if we move on the other case, FeSi was the last phase to crystallize, to melt, sorry. So this means that is the first phase to crystallize. But when we make FeSi crystal, their density is not that different from the melt that will move them. So they will not sink and they will not go up because they're buoyant. They will just stick around their position. And they keep on sticking around, we keep on making crystals. And so we have this situation that is defined as sort of like crystal mush. We have a lot of crystals with some interconnected liquid in the middle. And whether or not we can activate a geodynamo in this condition is unknown. So we still don't know if these can result in a magnetic field or not. But I hope each one in this room is understanding the relevancy of like having this kind of information that we can only get with experiments. So let's move on now to in situ experiments. So here I have the example of silicon carbide that was part of the work that I did during my PhD for carbon-rich exoplanets. So now, what is the interest in tracking, for example, the volume change of phases at high pressure and high temperature? This is important because we know how atoms are organized, and so we know how phases will be in depth in a planet. So in this case, also all of these are all experimental points plotted as pressure, volume, and the temperature is the color. And it's striking to notice how we have a jump here in the volume that is induced by a reorganization of the atoms. So instead of having like this bond between these atoms, now we are changing coordination, it's called. And these imply a big shrink in the unit cell volume. So we have this volume jump. This volume jump was considered to be responsible of a dichotomy in a SiC mantle that made two different convective cells, just because this phase and this phase has very different mineralogical properties. But so what does it mean? Like how we use this data, aside from saying that there is a volume jump. The way in which we use them is to fit equation of state. I think everybody here knows about equation of state and use probably equation of state. I have a couple of slides because I want to bring to your attention where are the pitfalls of using equation of state, and especially where are the operator dependency, because it is math at the end of the day, but it's math made by someone who decide what is the best solution. So there is this review about equation of state. Here we're discussing equation of state at ambient temperature. I don't even want to go in detail. The attention I want to make is that these are the two most used formalisms that probably everyone has seen in papers and so on. These are the parameters that we try to determine. V0, so the volume of the phase at 0 pressure. K0, how this volume change when we go in depth, so with pressure, and the derivative of K0, so how this volume change is affected by pressure. And the difference between this formalism is just a way in which we define the volume shrinking. So it's really trivial. But we have three parameters here that in principle, if we had perfect data set all the time, we will be able to define with our data sets, but we can't, and I will show you why. Then let's move on to high temperature data. We really need to consider also high temperature, because while pressure has an effect of shrinking the unit cell volume of a cell, temperature will try to expand it. So we'll need to consider the two effects together to really understand what's going on in minerals. Because if I use a 300K equation of state for a unit cell that is at 4,000 Kelvin, I'm not going to be representative of what's going on. And here, these are the two main formalisms. And I want to show that here we have three parameters and here too. So this means that when an experimentalist is trying to parameterize an equation of state of something, either they're defining 6 parameters, either 5, in an ideal world. So let's move on to like some actual data to show how things are applied. So first of all, I want to focus on this graph. Here we have pressure, volume. These are data at ambient temperature, so 300K. And first of all, these are two data sets. This is from my publication. This is from another person who worked on the same material. Two striking things in this figure. Both of us start approximately at 50 GPa. So this means that we don't have an experimental determination of the V0 at 0 pressure. So already the V0 of the 300K equation of state, it's either taken from other paper, either tried to refine depending on how you fit your experimental data. The other aspect is that in one case, the data set goes down to 200 GPa. In one case, the data set goes to 90 GPa. So when we are trying to fit an equation of state, we're drawing this line, and the bending of this line and the curvature of this line is given by the numbers that we assign to the parameter we are defining. And so this is the first moment in which operator dependency really matter. Depending on how I decide to fit this equation and which V0 I choose and so on, this line will have a different bend and a different like evolution in pressure. So this is the first sort of like fundamental operator dependency and potentially pitfall of just using equation of state from papers that maybe don't really describe well how things were done. And then this is moving to high temperatures. So still volume, pressure, and this is temperature. And in this case, the lines represent our model. So the lines are calculated with the parameters that I decided to use for my model, and this is my experimental data. And this is an ideal data set because we see that the lines really reproduce well the evolution of the data, also in this high pressure regime. But where things can go wrong, one example is this one. So this is 300K data for iron, pure iron. So there have been bazillion of people working on this. And we see that the experimental data sort of like all follow the same trend, if we want to say. But still, the variability of how we set the V0, so up here, gives this fun of lines in the low pressure regime, so up here, that translate in a divergence in the lines here. And we are at 200 GPa in this case. So still Earth core. Imagine like how big is this divergence if we applied it to like 500 GPa, 600 GPa to model super Earths. Like this can really have an effect. Then let's move on to other things that went really wrong with high temperature data, for example. This is one of my data set. These are still data for the FESI-C system, so the one I showed with the phase diagram. These are the experimental point, the lines are the model, and we got some number that sort of made sense when we were looking at it. But then when you go in depth, this is the high pressure side. You see that all the lines here are squished together. They don't even pass on the high temperature points. These points are kind of not really organized well. So this is a bad fit. And likely because the lines are so different from how the high temperature data are, is not even a representative fit for my experimental data. But here as well, operator dependency. I can refit all my lines and see that this doesn't exist, or I can trust that I got number that makes sense, and then use this data. And I want to show why this is important, because either we directly go from Eros and thermal equation of state to mass radius plot, or we use this data to inform the databases that we use for thermodynamic modeling to obtain sort of like the stability of different phases at different pressure and temperature. Then we use these to build planetary interior models and mass radius plot. So everything starts from the parameters that we use. Now that I sort of hope not make everyone too sad, I want to move on some perspective about exoplanets from my interior experience. And everything has been sort of said in the past days, but I want to make a sort of nice recap with images. So the matter of diversity, I think diversity is really important. And all type of diversity. We need to be considering diversity in composition, because like every single planet can evolve in a million possibilities. And we need to be considering the importance also of evolutionary path, as it has been said. But we also need to be considering diversity in size. So things might not be really super weird, but might be super weird in terms of size. And so some of this has been said. So diversity evolutionary path, what led to like the deep divergence between the Earth and Venus, like this sort of question that can be really applicable to exoplanetary systems. Diversity in composition in terms of not only ice and water. We have now this low density world that seems like might incorporate a lot of water inside, but also diversity in the main mineralogical components. Like people that knows me know that this is my sort of like go-to argumentation. But if we consider only the main planet building elements, so refractory, iron, magnesium, silicon, volatiles, carbon and oxygen, this is what we know. This is the Earth. And I hope I'm convincing you with this figure about the importance of at least trying to understand if we can move in these fields or we can't. But this can't be just coming from like mineralogists or modelers. This should be a sort of like joint effort into trying to understand if we can move there from the point of view of planetary evolution and planetary formation, and if we can move in these phases from the mineralogical point of view, like if we have other phases that we don't even know because we don't observe them in the solar system. And these, hopefully I've convinced you why this is fundamental, because all the large scale properties of planets depend from what we have in the interior. So in this case, for example, if we have a core, we might have a magnetic field, we might have a water layer, if we don't even have like a core, we might not have a magnetic field, so we're just a bare rock. For what concern instead difference in size, I want to draw your attention on the fact that phases made by elements that we know might be extremely different when we start looking at higher pressure. This is an example from the work of Claire Zurkowski. And this is only MgOs sort of compounds, but at a much higher pressure, like 500 GPa, 1300 GPa. So knowing how the phases are stable in this sort of really high pressure regime is fundamental, because we might discover, for example, in this case, that there are coordination that are not visible at lower pressure, but are really relevant for example, super Hurt. And we will know more about this with the presentation from Federica. So I want to close with this sort of funny slide to make people maybe more happy. And I think my main point is that there isn't a right way of doing things, but there should be a synergistic way of doing things. Experimentalists should do things like should collect data that are useful for the other communities, but we all should make an effort to speak with each other to really start being representative. And I want to conclude with like something that was said in all the breakout sessions, that we need more funding, so it's not depend on us. And with this, I welcome any question. I hope I've convinced you about the importance of experiments and interiors, and you're welcome to come and see me if you have more questions or discussion you want to make. Thank you very much.
Thanks so much for this very good, useful questions. Yes, Janina.
So you show us how the results of different experiments can lead up to different fitting for the equations of state. Do you have a solution then of what you should all do to have consistent data?
I think everything should start with everyone stating their assumption in their papers, so that someone from someone not from that specific field who is not an expert in that precise matter is more aware of what are the assumptions that are being made. I think in my case, trying to collect really good data sets is like the most fundamental aspect. And then testing the variability. Like when I fit equation of state, I always get close for months because I'm trying how everything changed with all the parameters. While sometimes I've seen work in the mineral physics community done like, oh, I will fit just this equation of state without testing out, like choosing one V0 or the other might affect the situation. So it's really, as I said, operator dependency. That's why I hope people are not too sad I don't have a solution, unfortunately. On my own, I'm trying to do things like explaining what are the pitfalls because I work with the exoplanets community. I think if there were more people sort of like working in these mixed fields, there would be more awareness and more interest in explaining where are the assumptions and not just saying my data set is the best. And so these are the numbers that you need to use. But hopefully we're going in that direction.
Other questions?
I think there's...
Yes.
Hi, great talk. What do you think the role of ab initio molecular dynamic modeling should be in terms of exoplanetary science research?
I think like ab initio as the fundamental advantage of speed, and it can really be informative on what we should be looking for or what be interesting to look for. But then I think there should be an experimental component to see if things are really that way. So I think there should be a collaboration. Sometimes it's easier to see like, oh, according to maybe this calculation, it's more interesting to start testing this direction rather than the other, but it can go also the other way around. So for like this eightfold coordination work, that's something I was part of this paper from Raj Dutta. We saw something really weird in the diffraction pattern, and then Raj started working with an ab initio person to sort of understand what was the effects. But everything started because we saw something really weird in the pattern that we didn't know how to interpret. So I think collaboration and discussion between the two worlds is like the key to go farther.
I think we have time for one quick question. May I ask this? Because you show nice variations in the equation of states fits, but some people here in the audience, they deal with uncertainties and observations for exoplanets on massive radius, and they maybe to appreciate the effects that would translate to uncertainties in mass radius, given the variations that you're discussing. Could you comment on this link?
Yeah, it's really depend how good is the fit and how representative is of the evolution of the data. In certain cases, I remember we did it together for this equation of state. So these errors on the number, this is the one that we used with Caro for my 2018 SIC paper. And what we observed was that, like, for the same radius, there was a 2 sigma variation in the mass that we were obtaining, depending on which kind of fit we were using for the equation of state. So it's something that I think need to be considered, not only the fit, but also the uncertainties on like these numbers. Sometimes if the uncertainty is low and like plus or minus 10 GPA is considered a low uncertainty for this kind of data that span this pressure range, these might not have an effect of the mass radius plot once we extrapolated higher pressure and temperature. But like when this number start becoming bigger, or maybe like things are different, it can have an effect. Also, already the uncertainty on the fit I make, not even like the type of fit. So like considering always this range when we're using an equation of state data, I think it would be interesting to see how things really can change in terms of mass radius.
Thanks so much. Yeah, and thank you again. I will show you now, we show you now an overview about the breakout sessions and where you have to go to get to the right breakout session. Oh.
That's right.
Okay. I think maybe you see them all. So cloud diversity on rocky planets is in E33.1. Learning from James Webb about rocky exovelts, it's in E33.3.